Let me just check. You can start the stream. I'll just check. Okay, so it's streaming? All is ready? Okay. So welcome everyone. It's our second incarnation of this workshop. We are very pleased to welcome all the speakers and all everybody else who's participated in this. For the first talk, Julian is going to give us a talk on quantum chaos in quantum gravity. And the workshop is designed hopefully to be slow-paced with lots of discussion time, lots of time for questions. So do feel free to interrupt speakers and ask questions in real time. In the long talks at least, this shouldn't be a problem. And yes, so I hope it will be a fun activity. So Julian, please, you can take it at your own time.
Okay, thanks Tim. So thanks for everybody for organizing this and for inviting me to Durham. Wonderful to be back after quite a long time. As some of you know, I've been here many times. In fact, there were these Christmas meetings around Christmas time when I was a student in Cambridge. And in fact, I was always in Collingwood College, so not that much has changed. Except that this building has changed a lot. So it's my first time in this very nice new building. I'm excited to see more of it. So, right, so of course the spirit is indeed I have a lot of time. So please ask any questions at any point and we can take side paths or explore things that you find particularly interesting. In principle, if things do go to plan, there will be a second part of this. So the first part is almost a little bit review in character. There will be a second part of this which will be whiteboard. And maybe we'll even manage to have a coffee break between the two. But even if I don't get to the second part, it doesn't matter. There's enough, I think, interesting things to discuss also here. So I'll start very basic. Well, actually, this slide is not so basic, but I will then go and discuss some basic things. This is the motivational slide. Why I'm actually bothering talking about these ideas of quantum chaos, what is kind of the problem that at least I have in mind. There is probably, it's not news to any of you that there has been this tension that has been pointed out all the way back in the 70s by Hawking between basically semi-classical gravitational physics and expectations of unitary quantum mechanics. And the two very famous manifestations of this overall sort of tension. The most famous one, of course, is what we refer to as the black hole information problem itself. So that was pointed out by Hawking, and it is pointing out that the evaporation process of a black hole, at least if calculated semi-classically, seems to be in tension with constraints, not just expectations, but actual constraints that you can place on such processes in unitary closed quantum systems. And one way of making this particularly sharp is this Page curve, where Page essentially proved a theorem on, let's say, the behavior of a unitary quantum system and the curve of this evaporation dynamics, which is certainly in contradiction with the naive Hawking calculation. But I'm only mentioning this for context. I'm not actually going to talk about Page curves today. And so not about the black hole information paradox as has been formulated first by Hawking and then made more precise by Page. But there are other observables which actually encode this conflict in a similar spirit, but in maybe more mundane quantities. So here we'll be talking about entanglement, entropy of radiation, and so on. Here, we're talking about just the long-time behavior of ordinary observables, such as two-point functions of quantum fields propagating in the background of such black holes. But higher point functions are also of interest. Perhaps we'll also talk about those. So the origin of these paradoxes. So again, the paradox here is that the long-time behavior of observables as calculated using semi-classics contradicts or is in fact in conflict with simple constraints of unitarity on the long-time behavior of such two-point functions. Well, I might say more about what those constraints are. But again, qualitatively, these paradoxes, they arise because we have been convinced by arguments of Bekenstein and Hawking in particular, but many other people, that the black hole itself, so the equilibrium state that is the classical solution of general relativity that describes a black hole, actually defines a thermodynamic entity. So in particular, we can define thermodynamic potential that is defined by this black hole. In fact, two names I also should have put there, presumably would have been Gary Gibbons and Martin Perry, who have also made very important early contributions to this. So it seems to make sense, at least, to think of the black hole itself as a thermodynamic entity. But then the question is, how does such a thermodynamic equilibrium state, so one that has associated to it an entropy, a temperature, and maybe other thermodynamic microscopic variables, how does this ever arise? How does this arrive as the end state of some non-equilibrium process? So how do we thermalize and reach these states? And this is where, so now the main technical tool comes in. I want to study this question in ADS-CFT, so this holographic duality between anti-de Sitter spaces and quantum field theories. So I'm, in that sense, not addressing the original problem that was formulated in asymptotically flat space, but I'm only talking about, let's say, avatars of this problem in asymptotically anti-de Sitter spaces. But that, I think, has been called a tactical retreat by Schenker, I think, at some point. But this tactical retreat comes with the benefit, of course, that we have this duality. So we actually have a specific way of formulating this question using what we call the boundary field theory. So this I put here for illustration. Actually, since this is a general workshop, maybe I can even ask who is familiar with this holographic duality, ADS-CFT? Okay, that's a pretty good, very good. So I don't need to improvise a lecture on this. So what we have is, so here I'm basically representing particular example, three-dimensional ADS, as this hot tin can. So there is the cylinder, and on the mantle of the cylinder is the boundaries where the boundary field theory lives. On the inside is where the gravitational dynamics takes place. We can study processes either from the point of view of the boundary or from the interior. And so the strategy that I want to pursue is that we study the idea of quantum thermalization in such a setup. And in particular, there will be a number of interesting relevant timescales that will link to quantum chaos that I want to point out. But what do I mean by study quantum thermalization? So that deserves a little bit of explanation. So this is the idea that you study an initial state under Hamiltonian evolution of the boundary Hamiltonian, let's say, which is out of equilibrium. So that is not an eigenstate of the Hamiltonian. And for example, with some collaborators, I argued some years back that you can set up particular out of equilibrium states, which I'm just symbolizing here with some operator assertions, which are such that one can argue that in the semi-classical limit, they create a shell of matter that collapses toward the center of this ADS space, and in fact becomes so dense that it forms a horizon and eventually a black hole. And this is what I'm showing here. So the idea is that the thermalization dynamics of some non-equilibrium state in the boundary, and it's a well-defined non-equilibrium state, is the dual description of the formation of a black hole. And if you wait long enough, eventually also it's, let's just say, evaporation dynamics. There's, of course, subtleties about evaporation in ADS. But I just want to say that in order to then address how does a black hole form, why and in what sense is it a thermodynamic state, and how could it possibly be in accordance with unitary dynamics, let's just do the Gedanken experiment and form the black hole. And that means actually that we're faced with a problem that is a very popular and generic set of problems that is considered in, say, even in the condensed matter world, namely that of quantum quenches and the quantum thermalization of a closed quantum system. And it is interesting that quantum chaos and quantum ergodicity play a very useful conceptual and technical role in understanding it. So this is, in some sense, the journey I want to embark on, which is study these kind of quantum thermalization dynamics and put them in the context of ADS-CFT and black hole evaporation. So now I'll go to the basic stuff. Yeah.
You want to understand the paradoxes of black hole by studying the holographic dual. Is that what you're hoping?
And in fact, I'm going to do both. So I'm going to first study the holographic dual, but I'm also going to then be able to translate this into gravitational language. But I think the point here was more that just mapping this black hole formation into a particular quench is already one, let's say, way of conceptually reformulating the sort of questions that arise here. And that's very natural if you think about it in this ADS-CFT way. But I don't know if your question was maybe...
No, I mean, so your ultimate goal is understanding the black holes.
So what I will do right now, is I will first go through some quantum chaotic dynamics, and in particular, I will make, I think, some new comments there, and they will identify some very interesting timescales that are related to certain things that happen because of quantum chaos. And those timescales, I will tell you how to describe them in gravitational variables later. But I think if you had started just from the gravitational calculation, you probably would not have had the idea of looking at these particular timescales, and also not the way of looking at them. But you shall see, I think you will see. So, so for this now, let me take a step back and talk about thermalization, but also in particular, of course, how it relates to chaos. So we'll be talking about the quantum picture, but just to set the context, in classical mechanics, we learn already in undergraduate that thermalization is related to chaotic dynamics. And in particular, the chaotic dynamics of the Lyapunov kind, at least at early times. So we try to understand the spread of the distribution functions of a classical system over phase space. And what is usually the way that people describe how the thermal state is eventually approached is that if you take two trajectories that may be nearby in the beginning, so their initial conditions only differ by, let's say, a small parameter epsilon, then because of the fact that the phase space trajectories have a tendency to diverge exponentially with the so-called Lyapunov exponent, you find that in the end, the end state that is related to this very similar initial state can be vastly different. And if you do that for phase space distributions, then via mixing and eventually ergodicity, this means that the system actually explores constant energy shells of phase space with equal probability. So you end up with a probability distribution on phase space, which is basically uniform on constant energy shells. And this is what describes to you the thermal state in classical statistical physics. So the chaos is absolutely crucial in arriving at a state that is uniform over phase space. However, the problem is that in quantum mechanics, things can't work like this, at least not naively. Because first of all, it is not very natural to think about phase space in quantum mechanics. But secondly, and perhaps more importantly, the idea of trajectories don't really make sense in quantum mechanics at all. And so this whole scenario here should at least be altered. Finally, of course, one thing that is often cited is that the actual equations, the Schrödinger equation that will govern it is linear, and so there can be no such nonlinear Lyapunov type effects, at least again naively. So picture of thermalization for a quantum system is actually substantially different. Although in the end, of course, you do find echoes of this also in the quantum mechanical description. So the way that we think about thermalization in quantum mechanics nowadays is actually via two frameworks, mainly via two frameworks, which I'm giving you the three-letter acronyms. So the eigenstate thermalization hypothesis and random matrix theory, ETH and RMT. And so, well, I will talk about both of them in turn, but before doing so, let me talk about some timescales. So again, we might start at some time t0, and then in the evolution of the system, there are, I mean, at least three, but three that I want to mention, characteristic timescales that are important. And by the way, I will say something in gravity about each of them, although what I say about scrambling will be short and mainly of review nature, well purely of review nature. So there is some time which is related to the spread of quantum information called the scrambling time. And it, well, I will define it in a second, but it has essentially to do with how the disturbance of one operator starts affecting larger regions of the system. And this time goes essentially as a logarithm of the microcanonical entropy of the system, log s. So this is a time scale that scales universally with log s. So I made that remark. I don't think I will go into the details, but this time scale can actually, in semi-classical quantum systems, be related to classical Lyapunov effects.
What are the units?
The units, well, I think I want to, so for example, a good unit is usually, let's say, the spectral width of the system. That will be one way that you can normalize all these time scales. So,
same with the temperature? Can I think of that?
I don't think it's always the temperature. No, I see. No, I don't think it's always the temperature.
What is the spectral width? What is this word?
Sorry?
What is the spectral width?
What?
What is it?
Yeah. So we usually talk about a quantum system that has like a bounded Hilbert space, and this is typically, let's say, the difference between the ground state and, let's say, the highest energy state that you consider.
Bounded, you mean finite dimensional?
Finite dimensional Hilbert space. Otherwise, also these timescales all go to infinity, by the way. So we do want to have a bounded Hilbert space.
About the particle in the box is not supposed to.
Particle in the box at fixed energy is a good system. Yes. So you have to look at the microcanonical fixed energy for a particle in the box. But that's true for any system that has, you know, where you can add, if you want, any bosonic excitation. Yeah. But in particular, particle in a box is a good example because you are in a finite spatial system. So the fact that you're in a finite box, that's very important. The fact that you can add oscillator modes as you want is not important because that you can cut off by saying I'm at energy, average energy E. Okay? But the fact that we're in a finite system, that is important, especially finite systems. So this goes...
Sorry to interrupt.
Sure.
And how do you then define this, what you call the spectral width? I guess it's defined by the average energy.
In this case, it should be the average energy, I guess, and which means that it's related by some transformation to the temperature.
Can you intuitively again explain the scrambling? Because I don't think I understand the intuition of that first time scale.
Yes.
Is it the coherence of some sort?
No, it's not the coherence. So there's two ways of intuitively understanding scrambling, what this time scale is. So the one that is not usually discussed, so maybe I'll say that, is that if you take your picture again of phase space.
This time scale doesn't exist for normal quantum systems, only for quantum systems with many particles or something.
You mean the scrambling time scale?
Yeah, you need like...
Well, let me say this first, and then maybe, I mean, I think you're right, by the way. But this is not the normal definition that people give. So, and then you take some wave packet, actually, So a minimum uncertainty wave packet, which means that it will have, let's say it's some coherent state, so it'll have a spread in phase space which is approximately 1 Planck cell. I don't know, you put your phase space, you separate into Planck cells, and then you try to localize your system, and quantum mechanically you can do only, because of uncertainty relations, you can only be like, let's say a coherent state will have the optimum between x and p spread. So you will be in some phase space cell, but then because of the dynamics, this will actually spread. The size of this will tend to spread out. And by the way, the rate that this spreads, if you're in the semi-classical limit, that has to do with Lyapunov exponents. But that's maybe not so important. But the point is that at some point, this will have spread into an order 1 cloud, which is so big that essentially you're not able to tell anymore which Planck cell it came from in the beginning. Okay? So
do you assume
the wave packet. The wave packet spreads.
Do you assume that you have obvious system here?
Yeah, sure.
But there is a new field theorem that precludes that.
No. Of course, the volume of the wave packet can spread.
Yes,
Of course.
not in phase space. Phase space, the volume is conserved. It's a new field theorem.
Ah, no, but sorry. So
You mean
maybe it just no. Maybe Zohar is right, and what it does, it just becomes very thin and long.
Yeah.
It's true. It becomes very thin and long, so it conserves the area,
Yes.
but it's still such that it's delocalized in one of the dimensions, so that you cannot tell anymore whether it came from any given initial phase space. So the fact that, let's say, one linear dimension, right, that's also, thank you for reminding me, that's also why Lyapunov comes along. Because it spreads, of course, in one linear dimension most effectively, which is the one with the maximum Lyapunov exponent. So the time scale that the wave package is spread of order 1 in that one linear dimension, that is a time scale which essentially is, by the way, lambda over h inverse times log of the entropy of the system. This you can work out just from spreading, for example, a minimum uncertainty wave packet. And so in some sense, the information has become delocalized on phase space. You don't know anymore where you started. The initial condition is washed out. But at the same time, well, this actually I don't think I can now, off the top of my head, I can explain why that is. But at the same time, this is also approximately the breakdown of the semi-classical approximation if you started with a semi-classical state. Okay. But let's say the thing that I can more reliably now vouch for is that it basically delocalizes initially well localized information over phase space.
It's not implied that one of the transformations.
I don't think that matters. What is the maximal Lyapunov exponent is certainly invariant, and it's only that which counts. That sets the time scale.
Does your system have to be open, or also it works for closed systems?
It only works for closed systems, as far as I know. Well, this definition. Well, I've never thought about it in open systems, but this definition makes sense in closed systems.
It's just confusing because for the classical story, one particle in a funny shape, like bigger, this phenomenon is spreading.
Yeah.
Here, log S, what is log S for one particle? Is 1.
I don't know. I don't want to think about one particle now. Let's think about a many-body system. In this case, it's fine.
It's just weird. The analogy doesn't work for one particle bouncing in a bigger.
Yeah, I don't think I can think of it right now. Maybe there's a way to make it work.
I know the quantum chaos, the way I heard about it like years ago, it was not defined through this story. It was defined through, just like energy eigenstates in the figure.
I will get to that. But there is a connection actually. But that connection is more at these time scales, and it's not at this time scale. And in fact, quantum chaos people, they usually get upset if we call this quantum chaos. But anyway, it's still an important time scale. And so, right, so we talked somewhat about the scrambling time scale. But the time scales that will play a more important role in the rest of my talk are actually these other two time scales that I'm showing here, the so-called Thales time scale and the Heisenberg time scale. So I will also try to define those.
And What is n?
And let me say that in a second. So when I know, well, I can also say it now. When I know the universal dependence with respect to entropy, I write it. This is true about scrambling in Heisenberg time. I don't know, and I don't think anybody knows the universal dependence with respect to entropy of the Thales time. So I'm writing it here with respect to n in one specific system. But let me get to that. So the Thales time and the Heisenberg time are typically much larger than the scrambling time. Although I'm not aware of a theorem that will tell you, for example, that there has to be a hierarchy between the scrambling time and the Thales time. That would be something interesting to explore, by the way, whether such a theorem could exist or bound anyway. But what is the Thales time? So the Thales time will be a time at which, so this is more related to the notions that Zohar already anticipated. So eventually we will talk about a system entering a phase where it is well described by a random matrix. This is called the quantum ergodicity limit, or the Thales time. And the timescale at which this happens is defined to be the Thales time. I will be able to be more precise about this just in a few slides. And then at this timescale, the system starts being well approximated by pretending that it is actually sampled from a random matrix distribution. And the final timescale that I want to mention, and also I will be more precise when I get to actually talking about it, is the Heisenberg timescale. And this is a very natural timescale. Again, if you take the average level spacing of a system, you take the inverse of the average level spacing, that is what defines the Heisenberg timescale, and this is usually exponential in the entropy. The reason is simply that there are e to the s many states, and so if the system has a finite spectral width, then approximately the spacing between them, at least the scaling with entropy, is e to the minus s, and so the timescale that is associated to it just by energy time uncertainty is e to the s, and that's why we call it the Heisenberg timescale. And as I said, delta is the mean level spacing. All right, so I'm giving a preview here now. So the goal is, of course, to actually describe these two timescales in more detail. This timescale, this is the last time that I will mention it. I'm only mentioning it for completeness. So the scrambling timescale was sort of the starting point for the recent revival, I think, of people's interest in quantum chaos from the chaos perspective, and mostly thanks to Titayev, Schenker, Stanford, and Maldacena. And essentially the upshot is that this has to do with what they called the butterfly effect in black holes, and it has to do with essentially the physics of shock waves and how the initial excitations are blue shifted to strongly affect the horizon of the system. And from this they basically define some sort of semi-classical version of the Lyapunov exponent, and this is a famous story that eventually has been linked back to work in the 60s by these Russian disordered superconductor physicists Larkin and Ovshinnikov. But as I said, I don't want to really talk about this. There is a nice gravity description of it, and it takes place at the scrambling time. But what I do want to talk about is what is the Thales scale in ADS-CFT, and how do we think about it gravitationally, and then finally also what is the Heisenberg timescale and how do we think about it gravitationally. And the preview is that the Thales timescale is the timescale at which, let me just say it, and then I might have to retreat a bit, at which non-trivial topology becomes important when studying the black hole. So instead of just looking at solutions of trivial topology, now I should also include solutions that are these two-boundary wormholes, which have more interesting topology. And that happens at the Thales timescale. And in some sense, this is the simplest deviation from the genus, the simplest genus, namely just the disk configuration. If you want to understand the Heisenberg timescale, then the effects that you're actually probing are what people like to call doubly non-perturbative in e to the s, so they're of the kind e to the face times e to the s. And that has to do in some sense with taking this non-trivial topology to the extreme and This is just to be seen in inverted commas, looking at infinite genus type contributions. But my goal is to describe both of these in detail and hopefully fill in more of the details for you, what I actually mean here.
Sorry, I missed. Did you say what n is in delta?
Sorry, I promised it and then I didn't. So delta I did, the delta I did describe. Delta is, if you take your system, it has e to the s states, and it has a finite spectral width. Then typically, the typical level spacing will be 1 over the number of states times the total spacing. And so since there are e to the s states, the typical spacing will be approximately e to the minus s. So the conjugate timescale is e to the plus s. But delta is that spacing. N I didn't say. So what I'm showing here is a Thales timescale that we calculated for SYK. And for SYK, the n is the number of fermions. And in SYK, it scales like n to the 1/2 with a logarithmic correction. But I didn't write an expression in terms of S, the entropy here, because I don't know one. And I don't think there is a universal dependence, parametric dependence on S. So I did the best that I could. I gave to you the Thales timescale in one particular system that's relevant to the discussion. So n here is system specific, and it's n of the number of fermions in SYK in this case. Yeah. Right, so good. So that's what I'm going to talk about. And I don't know in how many of these directions I will go. I might actually choose to describe more recent work. This is more, in fact, in the nature of review of other people's work. But of course, whatever interests you most, we can discuss. So now let's go to the usual definition of quantum chaos that people like more than, let's say, this semi-classical Lyapunov exponent. So so what describes a quantum system, of course, or a very important discriminant is its energy spectrum. What is actually the spectrum of energy levels? And so Wigner had the idea of trying to characterize the spectrum of a quantum chaotic system, and moreover, he had the idea that there should be some universal features that all quantum systems, chaotic quantum systems, share. And his proposal was to look at this quantity P of S, which is the probability of finding two energy levels. You look at your spectrum and you look at pairs of energy levels and you ask how far are they separated. S is the difference in energy measured in the average separation delta. Okay, so it's, if you want, I can of course write it. S is a unit that is very commonly used, and it will be something like one energy minus the other divided by delta. I think people put a pi here for convenience. So if S is 1,
for nearby energy levels, P of S is the probability of finding distance S for nearby energy levels, not for anything. You have to make a triangle when you define P, which is that they're adjacent.
Yeah. Pairs of, thank you. Adjacent pairs of energy levels. Yeah. You could also generalize it to look at triplets or four correlations and so on. Yeah. So if S is 1, then what we're looking at is basically one average which are further apart and pairs which are closer together. But the actual distribution actually, so let's say in any given quantum system, then what you need to do is you basically need to make a histogram, and you take all pairs that are separated by some small separation, you put it into this bin, and then by a larger separation into this bin, even larger separation into this bin, etc. So you get some jagged curve, but Wigner's statement was that this curve should be well approximated by the curve that he basically guessed. This is why we refer to it as Wigner's surmise, Wigner's guess. So what I've shown here is the so-called Gaussian orthogonal ensemble, because Wigner's guess it was not just out of the blue, he calculated it. How did he calculate it? He said, let us assume that we have, in some sense, the least amount of knowledge of our quantum system. That means that we can draw its Hamiltonian at random, but we can't draw it completely at random because it should at least be a Hermitian matrix. And he also said, let's say if you have time reversal invariance, then there should be a basis in which it's real. So this is basically what defines. Oh, and then we have the most amount of most lack of knowledge. So we just say the distribution of these matrices is Gaussian. This is the maximum entropy distribution of these matrices. And he calculated what would be the level spacing distribution under such circumstances. And he found this curve that I'm showing here in purple. And what is, let's say, robustly empirically found is that quantum chaotic systems, even with a few number of degrees of freedom, have spectra which approximate very well this Wigner GOE curve. And in fact, well, doesn't have to be the GOE, but let me not get into it, but one of the Wigner curves. There are only a few of them. Okay, so the energy levels follow approximately an RMT law on the scale of a few level spacings. You see I'm going maybe one average level spacing. I'm not going very far out. And what's sort of important maybe also for later discussions now is that the curve that well, two aspects of this. Let me say two aspects. First of all, the curve that I showed here in dashed lines, this is actually a system which is not chaotic and should not fall into this Wigner universality. And in particular, one can say that its level spacing distribution follows a Poisson curve. It's a Poisson law. But what's really important is really the difference between the behavior and the origin between these two curves. So the chaotic case goes to 0, which means that it's extremely unlikely that you have a degeneracy, that you have levels or even levels that are very close together. Whereas there is certainly a finite probability to find such an occurrence in a system which doesn't thermalize. So in other words, an integrable system. So there's two things that I want to take away from this. The universality of the chaotic systems and its description by random matrix distributions. Secondly, these all share the feature that the probability to find nearby energy levels is very low, and that contrasts starkly with the behavior of a system which does not thermalize, is not chaotic, is integrable, which is Poisson law, but in particular has a substantial probability of having energy spacings that are nearby. Okay, now.
Could you just comment briefly? You mentioned there are several Wigner curves. What is the difference, the distribution of the random matrix?
Very good. I will come to that again, but essentially this has to do with the amount of certain discrete symmetries that are present in the system.
Okay.
So if you have, for example, just Hermitian matrices, you don't actually get the GOE, you get what's called the GUE, Gaussian unitary ensemble. If you, on top of it, impose that it has time reversal invariance, then you get something like the orthogonal ensemble. You could also get a symplectic ensemble depending on whether you have premise degeneracy or not. So there are these three classical ensembles, and they basically have to do with very rough symmetries. This can be generalized, in fact, can be formalized a lot, and there is a theorem by Altland and Zirnbauer that there are 10 such symmetry classes. So there are 3 classical ones, and then there are 7 non-classical ones. But I think I will mention them again when I have a bit more technology to do so.
So just discrete symmetries are incorporated?
Just discrete symmetries in this classification.
I mean, is it of interest to look at systems with continuous symmetries, with larger symmetries? Not for the purpose of classifying the energy spectrum. So it doesn't really influence?
It does, but not in this way. So, for example, of course, if you have like charge, well, I'm saying this, of course, I'm anticipating quite a bit, but if you have, for example, just charge, okay, you want symmetry, then sectors of different charge don't talk to each other. And the fact that you don't have degeneracies, by the way, sometimes is conceptualized as saying there's repulsion between energy eigenlevels. They don't like to be close to each other. But if you're in different, let's say, super selection sectors, then they don't talk to each other. There can be no such level repulsion. So you have to basically symmetry reduce the system so that you're just in one block, okay, which is completely specified by all of its continuous symmetries. And then again, you will find this. And then you will find one of those 10 generalized Wigner classes. They're called alpha and Sandbauer classes. So it's not that continuous symmetries are uninteresting, but once we've reduced to symmetry reduced sectors, you find one of these 10 alpha and Sandbauer classes, and that's a theorem. So, but okay. So now I talked a lot about this stuff, but let me pull it back a little bit to the physics of black holes, because the way that this manifests itself is actually not typically through this curve, but in some sense through its Fourier transform. It's not exactly the Fourier transform of this Wigner curve. It's the Fourier transform of the two-level correlation, but these are related quantities. So the related quantity that people have been citing in the black hole context is the spectral form factor. And it's something that happens in time. I will give a formula for it on the next slide. But it's a curve. So for example, the spectral form factor, we call it k. When we look at log k of t versus log t, then people will typically show you curves like this, where you have some initial decay and then maybe some oscillations. It could be wild oscillations. But eventually, it settles down to behavior. I'm simplifying somewhat, which has this linear rising behavior ramp, and then a plateau where it's just flat. And I'm drawing in purple the kind of curve that you would expect if you said your system is exactly described by a random matrix. So what we're seeing here is that at a certain time scale, your actual system starts looking a whole lot like the random matrix system. And that time scale turns out to be the Tallis time. And from then on, you can describe your system to very high accuracy by pretending it's a random matrix. And in particular, this plateau physics falls into this time scale as well. And that's this Heisenberg time scale. That's where the thing just becomes flat. Superimposed on this, I say now, will be erratic fluctuations. But let me postpone that discussion for a little bit. But so what people have done, and here I might use the whiteboard again, is they have started to calculate, not for reasons I think of quantum chaos, but they have started to calculate these kind of quantities for black holes. And what they found was a very different picture. So by the way, not by the way, let me not say it. What they found is that if they calculated log t and this log k, and the way that you calculate it, maybe I put it on the next slide because, so it's essentially, let me first say qualitatively and then we can go to this. They calculated it, and you can calculate it by using sort of the standard rules of ADS-CFT because it is related to the partition function. That's why I wanted to flash this formula, but let's go one step by one step. And they calculated it, and they actually found something which just decays forever. So this would be like, let's say, the semi-classical gravity calculation. So the partition function times its complex conjugate at time t, calculated in semi-classical. And what you can say is that this is the answer that you get. And people have pointed out, people like Madasena have pointed out that this is problematic because at late times, simple unitarity tells you that it has to be at least, it has to be of size e to the minus s, but it cannot be 0. So the fact that this goes to 0, that it decays to 0, is one of these signatures that there is something strange going on. And so the question was always, what happens in this region? How do we actually get an answer that is compatible with unitarity bounds, which means that it cannot be exactly equal to 0. And what I'm showing you here is that quite generically, this is the behavior that is actually well described by the system when it's in its quantum chaotic universality regime. And basically, we want to understand how in gravity do we actually calculate this ramp plateau behavior. A, because it's interesting, but B, also because it addresses this question of the seemingly decaying behavior in semi-classical gravity. So we want to correct this calculation. We want to correct it basically because we need to have at least e to the minus s here by unitarity, but we will find that there is lots of interesting things to say about, as I said, how this interfaces with quantum chaos. Okay, so this is where the connection comes.
Classical gravity, that's equals infinity, no? So
No,
there's problem.
no, the black hole Hilbert space. No, no, no. This is just
Classical
a
gravity is h bar equals 0.
semi-classical. It's semi-classical, like Hawking's calculation.
Okay.
So we have to always understand when I say classical, I should always say semi-classical.
So maybe I missed that, but did you say what this spectral form factor is?
That's on the next slide. But the remark that is here that I still want to make is that it is difficult because it's a difficult task because it means that you have to do, in some sense, spectroscopy of the system in the literal, like old-fashioned sense, the energy levels. You have to resolve them. You have to resolve them at an accuracy of e to the minus s. And that's why that's a challenging computation.
Like, I understand technically what you're saying, and of course we've heard about it already many times. If you think about gravity as some sort of effective theory, like hydro, just to resolve individual states, there's one field, which is velocity field, that's it.
But the strange thing is that it does, as we will see. To some extent it does. So again, if you anticipate to the end of this, maybe the real puzzle is why does it do that? You know? But I have some remarks on that particular point too.
I mean, if you cover quantum effects in gravity, you should slowly resolve.
You should.
Right?
But what we will
it's
see, so
semi-classical.
the problem is that we are with different priors, we're jumping back and forth. So the conclusion will be that actually a lot of this you can understand in semi-classics. And there is no reason that you should, except that it works in many other quantum chaotic systems as well. But maybe we'll discuss that when we get there.
Sorry, from hydrodynamics, should you see
No.
individual energy levels
No.
like quantizing hydrodynamics?
No, of course not.
Most people would say no.
I think the philosophical difference is that you have the Beckett-Hawking formula. It's actually correct, right? So if your hydro told you the entropy density precisely, I would think then actually somehow.
No, it's at the same level of puzzle, but it is still. So in the end, the puzzle will be. Anyway,
Sorry, this is philosophical.
yeah, this is maybe for the end. So here is one way of thinking of the spectral form factor. You can just define it as such. It's the double sum of the Hilbert space. So each of these indices runs over all states. And what multiplies the Lorentzian time here is difference in energy levels. And so that's immediately the reason why if you go to very late Lorentzian times, you start probing smaller and smaller differences. And why is this an interesting expression? Well, I think the previous definition that I gave you is maybe more natural, but it's essentially equivalent, right? So
This f is k.
so if you take rho of E to be the spectral density, which you might say is a sum of E minus H, if I put a trace here. So okay, so it's just a sum of delta of E minus EI, I sums over the Hilbert space. Then you might be interested in quantities of the kind rho of E primed, and perhaps in a random matrix system you could average them, or you could think of averaging them over small energy windows or something like that. Or you do this histogram story that I have here, right? You broaden your definition of energy a little bit, you bin things. That could be also this overbar. So this thing, call that thing R2 of E and E primed. And of course you can write it as E is equal to some center energy minus omega 2, and you can write it as E primed is the center energy plus omega over 2. It's just a rewriting. Then you get an R2 of E center energy and omega. And if you Fourier transform this guy with respect to omega, okay, and maybe you want to integrate it over the center energy, this is a definition, this is maybe a different definition of the spectral form factor at a function time t. And if you write now, if you put in this definition with the Hilbert space sums, okay, then up to the factor of beta, I don't know why I put the factor of beta here, you basically get this definition here as well. Okay, so it is directly written, if you want, the two-level correlation function Fourier transform with respect to the difference in energy. But this makes it clear, this expression makes it clear that you can write it as z times z star, which I wrote once before. It's like the partition function times its complex conjugate, about analytically continued in temperature where you take beta plus IT.
So that's log k, or is it k?
That's K.
That's k.
That's K. Both
So
of these are
here
K.
it's called labeled f, so f beta is k.
F for beta is equal to 0 is K. This is defined here.
Oh.
But this is what quantum chaos people like to talk about, and this is what comes much more naturally out of the gravity analysis. In fact, in our community, if I'm not mistaken, Kyriakos Papadodimas and Suvaraju I basically introduced this at some point because of this tension here, and I think they introduced it somewhat without being fully aware that this was such a well-studied quantity in quantum chaos. And they introduced it like this, because this is related to the analytic continuation of the partition function. In that sense, it lends itself more easily to a gravitational analysis. Anyway, this is a good formula we can use. Yeah.
You're doing now in a complete system. You're not averaging, right? So it's literally just z times z star.
Yes, of course, but then when I calculate it, for example, in gravity, then everybody will ask the question, is this not the averaged answer or not? But of course, what I've written here...
Like, this definition is weird, because why do you care about z times z star? Just z, that's it. Like, one different multiplied by z star.
Yeah,
Why
I
are
agree.
we defining here as one which is supposed to be z star?
Because then you calculate this in gravity, and I think I will get to this in a second, and you find that precisely your, let's say, immediate intuition is not correct, seemingly.
Z star is z star.
I know, but let's talk about it when we get there. So I think we're jumping a little bit. So let's use. So the idea is, okay. So there is this quantity. I've given you some background on this from quantum chaos. The idea is to use now these quantum chaotic ideas to characterize the black hole microstates at extremely fine resolution. Okay? And precisely because of these questions, why is z star not equal to z times z star? Maybe this tells us something about the something quite deep about gravity. So the first indication that something interesting is going on came from these authors, Saad, Schenker, and Stanford. Yeah, wow. I might not get to anything.
2 hours doesn't look so long now.
No, but it's good. No, but it's great. I mean, that's great. Just keep asking questions. Very good. So, so the overall question is now: can we find the gravity description of this behavior? By the way, I noticed that perhaps because we're jumping so much, my talk was designed more in a way of here's this quantum chaos. Let's find the gravitational description of it. A different way of arriving at which was also, I think, more historically correct, is people were calculating some puzzling things in gravity, and as they went along, it was revealed that this somehow had to do with quantum chaos. So we could also just say, let's calculate some partition functions in JT gravity. That would be another way of motivating this slide, and then maybe we'll be more surprised. So what is JT gravity? Well, it's a two-dimensional model of gravity. 2 dimensions, again, one more tactical retreat. Okay, it's something that will be very amenable to explicit analysis. But it's a lot like Einstein gravity, in that it has almost an Einstein-Hilbert term and a negative cosmological constant. But for reasons of having too few degrees of freedom in 2 dimensions, you have to add one back in, this field phi dilaton. So this field phi is actually part and parcel of the definition of this 2-dimensional theory of gravity. And because the Einstein-Hilbert term itself, so just the integral of the Ricci scale at Ricci density, is topological, there is actually naturally, it's the Euler density in 2 dimensions, there's actually naturally also this term here, the Euler number of the manifold that you define this gravity theory on. And so S0 is just a coupling constant in this picture times the Euler density. And it turns out, as was shown by Saachenko and Stanford, but essentially mathematically established by Mariam Mirzakhani, that this theory actually has a topological expansion. So what you can do is, well, it's obvious that it has a topological expansion because the coupling constant couples to the Euler number. But what is interesting is that you can actually do the Euclidean path integral of this, and you can order it in this topological expansion. So that means that if I ask, for example, what is the partition function? The question of what is the partition function is the question in ADS-CFT now, what are all the infilling manifolds whose boundary is a circle of circumference beta? And you find that there is one where the Euler number is 0, which is the disk. And then there is a second one where you add a handle to the disk, and therefore the topology changes, and it comes with a weighting factor of e to the minus s0, but it has the same boundary condition. So it is this equally inadmissible solution to the problem of finding all infilling solutions that have a circle beta as boundary, which is the task that we were given by setting us the question of what is the partition function at inverse temperature beta. So you have all these solutions here. But in some sense, more profoundly, it becomes interesting when you start calculating products of partition functions. And that's where we're going to, that's before the break, let me discuss this. That's where we get now to some of the questions that were already raised. So we are now given the task of, let us say the boundary condition is now I have 2 fixed temperatures. So I give you 2 boundary circles. I give you 2 boundary circles of length beta 1 and beta 2. And what are now all the solutions of this theory that you can find that fill in this bulk in some way, this question mark? And well, as I said, Mirzakhani basically did that work for us. And following her work, you find that there is not just the product of 2 of these or 2 of these. There are also solutions which are very different in nature, which are actually connected. So there's one and the same infilling solution which connects one boundary to the other. And they are also, of course, by including boundaries and so on, you can calculate also their Euler numbers, and you will find that the first non-trivial one comes in at order e to the minus s0. So now, what we have found is that the product of 2 partition functions calculated in gravity is not the product of 2 results that you get for the one partition function calculated in gravity, because then it would have to factorize. It would be z of beta 1 times z of beta 2. But this is manifestly not the case, because there is this contribution and infinitely many others like this, which spoil the factorization.
It's because there's something over gravity.
Yeah.
You're averaging over gravity.
Well, but no, the averaging that you set in there is not obvious. I mean, and that's actually the whole debate that's still going on. Is gravity now secretly slipping an average in there? You seem to be concluding yes, but let's continue with it.
Something is happening.
Something is happening.
Product of 2
Yeah.
numbers is
Of course.
product of 2 numbers.
Of course.
Of
course.
You're using semi-classical gravity. So the product of 2 numbers is not equal to the product of 2 numbers.
Yeah.
So semi-classical gravity is wrong. End of story.
Yeah, I was turning one out.
So you want to conclude your talk
No.
now?
Certainly not. But we can take a break, I think. But now I'm in a good point to state something which we'll get to later. So what we can do though is we can just look at what is the physical effect of this guy. What does it do? So for example, we can take the inverse Laplace transform of this. This is kind of undoing, when I first defined the spectral form factor. Okay, so to get back to this is like defining again some kind of correlation between 2 energy levels. Right? If you take the inverse Laplace of this function, then you get to well, you get to a contribution to, of some correlation between two energy eigenlevels. And what you get is you get a contribution that goes like a singular contribution, difference of energy squared, plus stuff that's regular in differences of energy. And if I know where to Fourier transform this guy, this is what gives me a contribution that is linear in time t. So this guy here, I don't know why I didn't write it. Oh, I did write it, yeah. Sorry, this gives the ramp. This contribution precisely gives the ramp. And I'm saying more actually here. Because the ramp isn't just linear, it actually is linear with slope 1. And that slope 1 is a consequence of this random matrix universality. So you don't have a choice. You can't get 1.3 or whatever. And if you put this in the right units, so the units are always with respect to delta, and that's why I slipped this pi in here, okay? This comes out with unit 1. So this is actually the ramp. This is exactly the ramp that you would have predicted from this quantum chaotic expectation.
So all other genus doesn't give any corrections?
So, good question. This is actually the unitary class. And in the unitary class, the answer is yes. And there is actually some non-renormalization theorem where this happens. In the other symmetry classes, this is not true, and these corrections are actually very interesting.
What's delta in JT?
Delta in JT gravity. It yes, no, but there is some energy scale. So I'm just trying to see what is the energy scale here. I'll think about it in the break because I want to get to the break. But it's of course it's e to the s in terms of entropy scaling, e to the minus s in terms of entropy scaling.
The average of two that's is positive. Why do you define minuses?
I don't know, but I know that it has to be there because well, I can only give a technical answer. I'm not sure it's very interesting then. But the reason is I said that you just take the straight Fourier transform. It's not quite right. There is something to do with analytic continuation. Okay? And if you go through the actual mechanism that you have to convert this into a time-dependent quantity, in order to have plus 1 times t, this has to be minus this quantity. I don't have a good intuition for this. It's perfectly honest. Yeah, but still. I'll think about it, but let's get to the end of this slide. So what we found is that for some reason there is a connected contribution to what should just be the straight product of two partition functions in this version of gravity. And that's the kind of thing that you find not in individual quantum systems, because in individual quantum systems it's that clear. You know, you just calculate z and then you multiply with z, you get a product. You get it if you average over something, either the Hamiltonian itself or some parameter or maybe some energy windows. But that means that somehow this gravitational solution here has forced upon us at least the necessity to think about averaging. So gravity contains these wormholes which strongly suggest an average over an ensemble of quantum systems. And there are two ways that you could think about it. One of them, I guess Zohar would maybe say semi-classical gravity is wrong. But we can also just say, so it's true, it really is an ensemble, and we should think of the bulk theory as being dual to an ensemble of boundary theories. Or that there is actually more to say about how ensembles and chaos come about. And of course, that's the route that I want to take. And maybe it's not a good idea now to try and anticipate everything that I'll say in the next hour. So shall we take, like, I don't know, a break until, or what do you want to do, 10 minutes or 15?
Depends on how much you want to do.
Yeah, no, I mean, I think we can take until 1:15 and then...
Okay, so 45 should be enough for you?
Yeah, sure.
Okay, let's thank Julian.
Not done yet.
I know, but okay, maybe I should. Okay, let's not thank him. Yet, we'll take it back. Okay, can you pause? I think you can pause the stream. I have a very professional thing here. Okay, so you're just gonna do that?
We
Okay.
can do that,
Okay.
yeah.
Yeah, we can do that. So is it picking up the microphone?
No.
Okay, good.
Feel free to discuss everything.
Okay, thanks. Yeah. So sorry, you're asking questions.
No, no, I mean, for me that's fine. It's just turning into more of a review. But
Lucas, should we close the door? We should, yeah. You can go in.
What's the
I have no idea.
We can pair with someone else.
Well, to put all of your teachers, so why don't we always get teachers?
No, no, yeah, I understand. You're already allowed to pair projects, pair with someone else. Project supervision when we go.
That's really after that. Yes, and the other thing might be you would accept it probably, but just have as an aspiration in the situation for all the other teachers. I think that's literally, literally impossible.
Which might be just make the project optional for, maybe 10% or 15% of the students will actually get something out of it.
I'm slightly hesitant, I'm very fond of the project, but
But
anyway,
yeah,
that's
forms of,
that's a slightly
whatever.
side issue though, because I think even without the project, at the moment I know it's such that
Probably, yeah.
feel like a sort of sharp pursuit. I think the people who do the research going to just get this over with and not maybe others are free.
Yes.
That's the
Yes.
don't know, we'll see.
I'm frozen, I think, so long as maybe this is not restarted.
Oh, yes. Let's see where Luca is, because I don't know how to do that.
Okay. Well, I can't change the slide, so. We could probably make that work.
We could spend 45 minutes talking for the second talk, I think.
And some with more abstract.
Okay. So, yeah.
Is it working now?
Yeah. No, actually, the clicker isn't working.
Oh, sorry.
Maybe it's,
This is a matter of changing the. Is it?
Yeah, no, it's working. So, okay, so now I am actually going to change gears a little bit. So far I've basically been reviewing work of other people, but now I'm going to talk a little bit about some of my own work. And I think it will interface in a useful way. So this is work together with Alex Altland in which we tried to understand some of this, or in fact, I think the entirety of the story that I talked to you about on the quantum chaos side, using the principles of effective field theory. And to do so is very useful to look at correlation functions of spectral densities, obviously. And so for this, we introduce some generating function of spectral correlation. So if this may not be entirely immediately obvious why this works, so let me just show you one thing, which will make it more obvious. So what are these determinants? The determinants are just gadgets that if you differentiate them, so you should think of these z variables as energies. But so for example, if I differentiate the determinant like this, so this H will be the Hamiltonian of a quantum chaotic system of interest. If I differentiate this, then I get back the determinant at first. And then what I get is I get the trace of the inverse of this operator, C1 minus H. And the trace of the inverse of this operator is, of course, known to many of you as the spectral resolvent. So this might be R of C1 for resolvent. And in particular, we can extract from the imaginary part of R of Z1. Okay, we need to actually put some kind of I epsilon here. We can extract, I think, up to a factor of pi. We can extract from this trace of delta Z1 minus H. And you see this is actually, I wrote this quantity once before, this is a definition of the spectral density. So this resolvent itself is a useful gadget that allows me to generate insertions, if you want, of the resolvent. And the resolvent is one analytic continuation away from a spectral density. And now the reason why I have determinants also in the denominator is that I ought to write something like determinant of Z2 minus H here, evaluated when Z1 is equal to Z2, and that for me solves this normalization problem that I would have otherwise. Okay? So each ratio of determinants serves in some sense as a gadget to generate a normalized resolvent, and from the normalized resolvent, I can go to the spectral density, for example, relatively conveniently. And so what I've written here is a ratio of two pairs, sorry, a product of two ratios, which is the thing that you want if you're interested in two row correlations, so two resolvent correlators. That could be generated to, let's say, 4 if you have 8 determinants and so on. Okay? So I'm giving you the one that is appropriate for the spectral correlations of pairs of eigenvalues, because this is the quantity that we will most want to connect to.
What are these plus and minuses?
Yeah, this is related to the analytic continuation here.
The IF.
And the reason is that, again, if you want to have row-row correlations, then the analytic continuation you want one in the upper half plane and one in the lower half plane. And this is what I've indicated here. So, of course, this idea, including this idea of the symmetry, goes back to all the work in the mesoscopic community, in particular associated with Wegener and Yefetov independently. So what we point out is that this ratio can be rewritten in a way that makes it apparent that essentially the fact that you have 4 times the same Hamiltonian, because you're interested in the same quantum system here, it has a graded unitary symmetry, which basically rotates these 4 H sectors into each other. And because, okay, a determinant in the numerator can be associated, can be exponentiated by introducing auxiliary fermion degrees of freedom, and a determinant in the denominator by having auxiliary bosonic degrees of freedom. This is actually the origin of why there is a graded symmetry, 2/2, that rotates these. So it rotates, it is in some sense a supersymmetry. And in fact, Yefetov even used the language of supersymmetry for this. So, so what we do is basically we write this.
How do you exponentiate the denominator?
Well, you can always introduce auxiliary degrees of freedom of the form. So you can write something like, so you can write the determinant of z minus h. So if h is an n by n matrix, we call it d by d, then you can write this as an integral over psi bar psi Grassmann vectors of dimension d, e to the psi bar z minus h psi. It's a simple Gaussian exponentiation. And then you have a fermionic vector of d Grassmann variables for each determinant in the numerator, and you have the same for bosons in the denominator, because, you know,
Bosons you get absolute value.
Is that a problem? No, I think it's fine. Yeah. So the point is that this expression here will have this symmetry acting on it, where basically I'm rotating. Now I can actually write it. So I will have some graded vector, which I might call capital psi. So I will introduce, so therefore it's not so visible. So what I will, in general, I will introduce some graded vector capital psi, which is just my fermions for each of the determinant. So let's call them psi 1, psi 2. And then my bosons for each of the determinants phi 1, phi 2. And this is a vector which is here it's 2/2 graded. 2D fermions and 2D bosons. And it turns out that because this H is the same in each D by D block, I can rotate this by sending psi to U psi. Where U is basically an element of this. Sorry, am I doing something?
Just some technical.
Okay, where U is essentially an element, let me call it T, in this 2/2 times the unit matrix on the D by D indices, right? So this is homogeneous on each of the D by D indices, but it rotates those sectors. And of course, psi bar goes to psi bar U. However, this causal symmetry, this will be broken spontaneously in this way. And why is that the case? Well, let me first say what's on the slide, and then I'll write some few more lines here. So the idea is that because there is this symmetry group and it's breaking, then you can write down the low energy theory of the Goldstone bosons of this symmetry breaking. And this Goldstone theory is what we call the effective field theory of quantum chaos. And we can show that it reproduces the physical content of random matrix theory, which I will do in a couple of slides. And so the theory that reproduces this will be a nonlinear supersymmetric coset sigma model, where the target space is just going to be, in this particular case here, U2/2 mod U1/1 times U1/1. And so it will be a G over H coset space sigma model. And in fact, getting back to the question I had earlier from Tim, by the way, you could work much harder, and you could show that you can also do a symmetry classification according to the discrete symmetries of H, and you would find that there is exactly 10 admissible symmetry groups and breaking scenarios, one for each of these universal so-called Altland-Zirnbauer symmetry classes. And this is basically a classification, in this case, of the geometry of these Riemannian symmetric superspaces. So why this symmetry breaking? Sorry?
I triggered a question for you. Why is this called causal symmetry?
Oh yeah, well this is something that I think we came up with. And okay, actually, yes, I can give the reason for that. Because you can write rho of E. You can write that as, I wrote it as the imaginary part of this guy. So the imaginary part of the propagator. So it is the advanced propagator minus the retarded propagator. So if you conclude that the advanced propagator is always equal to the retarded propagator, so there's a symmetry between the causal sectors, then rho will always be 0. But we want to have correlations between rhos in regions where it's non-zero. And so in each of these sectors, there has to be an asymmetry between the plus and minus sector, which is what we call this causal symmetry breaking. But it also resonates with chiral symmetry breaking, because there's actually a nice analogy between this and the way you think about chiral symmetry breaking in QCD and causal chiral. I don't know. Anyway, but the physical reason is what I said here. So I was going to say a couple of words about the symmetry breaking.
What's that little omega?
That's just the energy difference. Good question. But of course, in the end, I want to write it as a function of Z1 minus Z2, and I might define that as omega. The reason being, again, that the thing I want to probe is energy differences. And so I differentiated it here, and I said Z1 is equal to Z2. What I actually want to do is I want to differentiate it twice and then set Z1 is equal to Z3 and Z2 is equal to Z4, for example. But then there's still a difference left, and that's the difference is omega. So,
Sorry, I understand what the scheme is Z1 is not equal to Z3, then S is equal to 1. I actually have a question. So we do this rotation, the Z
yeah,
is different.
I think what you're, but first say your question. Sorry.
Yeah, no, sorry.
So the point is, it is actually a lot like chiral, the chiral Lagrange in QCD, because indeed there is a small explicit breaking, which is the energy difference. And that's like the quark mass in QCD. That was your question?
Yes, and but so just in units, why is it omega small? So it's omega much smaller than you want.
Yeah, no, but that's precisely the point, is that I want to look at Z1 minus Z2, which is of order delta. And delta is order e to the minus s. So it's very small energy differences that I'm interested in.
Understand parametrically of how much unity omega d is.
So, good. In the unitary case, for example, in fact, I can integrate over the whole Goldstone manifold. I can do the integral explicitly. So in that sense, I can take omega to be even of order 1. In general, it's just the perturbation theory just breaks down and omega is of order 1.
Can I ask this question? This is today's integrating a 0 to 0 dimensional system because it's just a big matrix. Is that the way to think about it, or?
The way to think about it is that the symmetry, in fact, will always be restored.
Okay.
But the way that it's restored is also interesting.
Okay.
I will comment on that too.
Okay. But it is basically like there's no notion of the time. The notion of time is
Correct.
in Z hat. And there's no notion of space.
Correct.
Correct.
In this version. There are also souped up versions where you do add space, but let's not get into it. So I did want to say one more word about why is there a symmetry breaking. And that's related to what one actually wants to know. So now we have a simple theory which is essentially of the form e to the, well, it depends on how you define your conventions, but this psi bar, and then you have z, which is now a matrix, minus h, where h is, if you want, sort of 4 times tensor psi. Okay, because I have for each determinant I have one h, so I have block diagonal h, 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 and then z will be a matrix which is a diagonal matrix where I have z1 d times, z2 d times, and so on, and z4 d times. And so this theory is just a Gaussian. I mean, there's nothing interesting here, in some sense. So what we need to do is, so first of all, we integrate this, of course, over my psi is psi. But what we now want to do, and this is really very important, is let's call this guy, I call it capital Z, which depends on little z, which is a matrix. I'm sorry about that. But how should I say this best? So we now do have to do some coarse graining or averaging or whatever you want. So for example, we could try again and implement exactly this, sorry, I'm not going to go back to all the slides, but we could do, for example, the spinning. We are a little bit unsure about what is our precise energy, and we bin states that are in a certain window. Or we could have, for example, that this h depends on some useful parameter that you can integrate over. Or there could be some very, well, you can even apply this to random matrix theory, which of course you have to do at some point because you want to map it to the physical content of R and T. So just in a test case, we also have to do it where H is a random matrix. So for example, if you do integrate this, this is the easiest thing to do over some P of H dH. Okay? And then again, for sake of simplicity here, if you imagine that P of H is just Gaussian quadratic, the Wigner case, so e to the trace H squared, let's say, then you will generate, but in general, you will just generate nonlinear functions of psi bar psi. So for example, if I integrate it over this distribution here, then what you would get is you would get a term that is of order psi to the 4th. So what you get is you get some nonlinear in psi interesting theory. And the point is that this theory is the one that breaks the symmetry. Okay?
To understand what symmetry breaking is, just ignore the integral, it's not even quantum mechanics.
Yeah, actually, I'm not completely sure quite how to say it, but one important point is that the symmetry will always only be broken by the mean field. But if you actually, for example, do the full integral, it will restore the symmetry.
Yeah, maybe the right
And that's important actually.
Maybe it's an integral with a huge parameter and it's a saddle point.
It's a saddle point, right?
Yeah.
Correct.
So you mean if you take strict Radian limit
Large D. Large D.
large D.
Well, sorry, I wrote D because I was saying the dimension of the Hilbert space is D. And that's not always the same as n. N is usually some parameter, like it might be 2 to the n is D or whatever. But, right.
I mean, superficially, the side feels like replicas, and then there's replica symmetry breaking. Mathematically the same. It's literally the same mathematics as was before replicas.
I think that you're right, but we're using the supersymmetry method precisely to get around the replicas. And in fact, a lot of the statements, particularly at the non-perturbative level, have not been made using the replicas because actually the mathematical structure is more complicated. So the map too is not quite one-to-one. Okay, but so the important message that I wanted to give here is that what all of these nonlinear theories, all of these averagings have in common is that they break the symmetry and that they break it in one of these 10 allowable patterns, which corresponds again to the classification of the universality of random matrix physics, but now rewritten in this saddle point, or I use the word symmetry breaking fashion. And that's very nice because it associates very clearly with individual quantum systems, of course via this step here, okay? But it associates to individual quantum systems in a very clear manner the physics of random matrix theory. So for example, I think I will, in 2 slides, I will tell you how to think about the spectral form factor in this way. And there, this physics of symmetry restoration is actually very helpful. So first the saddle point approximation, and then the full symmetry will be apparent. That will be actually very useful. So, right, so let me give you some general statistical physics lessons then, which we may conclude so now, and let me also give you a slightly different perspective. So first of all, what I've told you about is actually on the bottom of this slide. So I usually like to summarize it with this quote by Dumas, one for all and all for one, is that in this case, one system has the same effective field theory as the average over many systems. And this is one way of understanding how one quantum system can actually show this random matrix universality. So this chaos effective field theory says that random matrix universality arises in a very wide array of contexts. So for example, you could do explicit averaging, you could do some coarse graining. It could also be, so this is suggestive, and maybe we'll discuss about this later, your ignorance of the actual details of the microstate spectrum. Or you could not want to resolve it, and you still might want to say something effectively about the microstates. That's what I call laziness here. I want to make this one remark, which looks a little bit out of context now, but may be useful later, is that there is a way of constructing this sigma model, not in the way that I showed it, but by semi-classically quantizing a chaotic quantum system. So this has been done in a very limited range of systems, but what you actually notice there is that you can get this full effective field theory just by, in some sense, bootstrapping away from semi-classics. This is called the periodic orbit theory. And in this case, the spectral reach, meaning the spectral resolution that you get just from semi-classical quantization, is actually very puzzling. Sort of maybe intuitively shouldn't work. I just wanted to make that remark. There is this thing called periodic orbit theory, and maybe we'll use it in some discussion later. But another way of thinking about the same lesson, if you want, is this ETH way, which I mentioned right in the beginning, but didn't say much about. That's actually very central to the way that Daniel, David, and Bauer and I are thinking currently about the whole story. But I don't think I will have time to talk about this. But the general lesson is still important. So also this eigenstate thermalization idea shares this mantra, one for all for one, because what it is saying is that also individual quantum chaotic systems have some statistical, there's value in thinking about their spectrum statistically. The way that it's encoded here is basically by saying, if you take some operator that is local, for example, and you look at its eigenvalue in typically highly excited eigenstates, then it has some diagonal contribution, which is a smooth function of energies, and actually turns out to be the microcanonical average, but that's not important for my comment. My comment is that the off-diagonals are entropically suppressed with e to the minus entropy over 2 times some smooth order 1 function. But this thing here, RMN, is itself a random matrix which has mean 0 and unit variance. So also here, I'm thinking about certain properties of the spectrum statistically, even though I want to apply it for one system. And I want to remark that that is actually manifestly the case. And I checked this with one of my former graduate students, Manuel Bielma, that if you look at our beloved SYK system, where we usually average over couplings, right? This satisfies this eigenstate thermalization ansatz even if you freeze the couplings. That's important. Not just averaging over couplings, but it actually freezing the couplings. So that's again an explicit example of this. And so I want to say that what statistical physicists have over many decades in some sense studied, and maybe we formalize it somewhat with this effective theory here, is that the kind of puzzles and things that we want to think about in gravity, they have at least there is at least an idea of a framework that addresses them satisfactorily without having to go to an actually explicit underlying ensemble. So in order to link this to gravity, which is what I want to spend the rest of my time doing, let me point out one more thing about this effective field theory. So it still ends up being a matrix theory because the degree of freedom, the gold star, the degree of freedom is still a matrix. It's a small matrix. It's in this case a 4x4 matrix, graded matrix. So it's not a huge 4D by 4D matrix, but it's a 4x4 matrix. And as such, you can still classify its diagrammatics by topology. And that's what we did. And what we showed is that generally, for the general symmetry class, the singular in energy, when two energy eigenvalues collide, in the case of the 4-determinant ratio, you can classify the singular parts of all of these diagrams by the topology that contributes. So in particular, everything I've said so far was around one saddle point. There's a second saddle point, which I will say in a second. But let's look at the first one, the so-called standard saddle point. You find that the first diagram that contributes gives you a 1 over s squared singularity, which should remind you of the one that I showed you earlier. And the diagram in this, we call it flavor matrix theory, that computes it as the topology of an annulus or a cylinder or a two-boundary wormhole.
Standard means symmetry breaking.
Both of them break the symmetry.
Different ways.
Yeah, I'll show in a second. And then there is potentially, so this relates to Tim's question, corrections that would go like 1 over s to the 4 and so on, and then they're related by the number of handles you attach to this cylinder diagram. So for example, in the unitary class, there's actually a theorem that shows that the actual coefficients of all these terms is 0, but in all the other symmetry classes, they do give interesting contributions. And then there is a second saddle, I will show on the next slide where it comes from, I'm pretty sure, which has the same topology, but the actual coefficients are different. And this saddle has an action which is actually e to the 2I times the energy difference in units of delta. So S is this little s here, this S here. I think I'm showing it here. And you can also calculate it, and so the topology is the same, except that it's around a different saddle point. And if you add up the leading contributions, which again in the unitary class are the only ones that are there, you actually reproduce this famous sine kernel of Dyson that he wrote down in the 70s. So this is some famous result of the universal level correlation, and it comes because you have 1 over s squared singularity from the wormhole diagram, and all the others are absent in the symmetry class. The standard saddle breaks the causal symmetry but leaves the supersymmetry intact, which means that its action is equal to 0. And then the second one has a non-trivial action, and the relative phase gives you the sine oscillation. So there exists a topological expansion of this physics of random matrix theory, and this topological expansion gives you the leading singular parts of all of the diagrams, and we will get back to that from the gravity perspective. So here is the question also about whether symmetry is really broken and so on, and also the second side. So what happens is that if you look at the start of this ramp, so I've only focused on the universal part now. Then this comes from doing perturbation theory around a saddle point. So this U2/2 divided by U1/1 times U1/1 turns out to be the fermionic part is actually this compact 2-sphere. The bosonic part is hyperbolic 2-space. And you fluctuate around the north pole of this sphere, and you fluctuate a little bit also in this hyperbolic space. This is what we call the standard saddle. There actually exists a second saddle where instead you're not on the north pole, but you're in the south pole of the sphere. Both of them break this causal symmetry, but only one also in addition breaks supersymmetry. And so the idea is that as this parameter becomes larger, you go into the regime where, in fact, you should try and do the full integral non-perturbatively. You can do it first by including only contributions from this other saddle point, and that's okay. And you still see the symmetry being broken at the mean field level. But once you are here around the Heisenberg time, which is actually when the perturbative expansion parameter is equal to 1, that defines the Heisenberg time here, you really need to do the full integral over the sigma model manifold. And in our unitary class, we can in fact do it. And what you find is that the symmetry is now restored. And the fact that the symmetry now is restored translates immediately into this plateau. Let me say maybe a few words why I say immediately. If the symmetry is seemingly broken, then what happens is that the poles of the spectrum have condensed into branch cuts. And so you don't see individual energy levels. This is the physics along here. But once you have enough resolution, you actually see the individual poles. And when you're in individual poles, then this symmetry is with almost certainty never broken, right? Because it's no meromorphic function. And you actually see the restored causal symmetry is a sign that the energy levels are now all separate. Sorry, you have a question.
So S, so you're saying large S means that the energy difference is large?
No. Yeah, what I want to say that the energy difference is getting smaller as I go to later times.
So maybe it's S minus 1, which you write down the hyperbolic. Just conclusion actually yes, that you have an expansion over S and also yes.
Yeah.
So it seems to me that S is large when the difference between the atoms is large. Is that correct? So that's why you get rid of the expansion also.
It's true. Yeah, maybe I made a typo here. Yeah. Just trying to remember why.
So time is explicit breaking parameter. Yes. met the explicit breaking parameter was time.
I'm not sure what you refer to now. So
Yeah,
there is an explicit breaking because of energy differences.
And then it becomes time.
Ah.
Yes, inverse time.
Yeah, inverse time.
Yeah. So
you want the difference between energies to be sufficiently large for the expansion to hold, but at the same time should be smaller than something because it's an explicit breaking.
Yeah.
What's the parametric?
What's the parametric?
Yes, there is an expansion 1 over s. It's clearly the energy difference to large is also the explicit breaking parameter, so somehow you don't want it to be large.
I suppose. I don't know. I don't know off the top of my head now. Okay. So good. So let me let me use the remaining 10 minutes to talk about the out-of-the-box story of this. So I suppose the things that you can do with this is you can not just do spectral correlations where you get this ramp plateau physics. You can also explicitly link it to one microscopic model, which is SYK, which is quite useful, and it has useful ways of understanding, in particular, the early time physics and how it connects to late time physics. But then one interesting thing which I have not had the time to talk about at all is there's not just statistics in the eigenvalues, there's also statistics in the eigenfunctions. So there's wave function statistics. And that's one of the things, for example, which relates to eigenstate thermalization and OPE statistics and so on. But I do want to talk a bit more now about a bulk understanding of this. So now let's formulate these things here in a language that connects to the JT, to the JT gravity that we introduced before. And so from the JT gravity point of view, the structure that we want to understand is actually the universe field theory. That's a notion that was actually introduced in the 90s by people thinking about 2D gravity. I read it first, I think, in a review by Ginsburg and Moore. But why is it actually, what is this thing about universe field theory? It's because if you think about a two-dimensional universe, then the spatial slices are going to be one-dimensional curves. So each of these boundaries, if you want, or each of these slices of which you give boundary conditions, is like one universe at a fixed time. And what we want is we want to have a theory which calculates correlation functions between these boundaries, so between these multiple universes. And moreover, we want to label them by fixed energy boundary conditions, E1 up to En. Of course, we only needed 4, but we might as well do the general thing. And so we want to have some generating function in the bulk, which is labeled by sources, each for each fixed energy insertion on these boundaries. And we want it to generate for us all the contributions with any genus on the inside. And so note that in some sense this chaos effective field theory is such a universe field theory, but it's a very trivial one because I have no metric information. I told you that I just did sort of some 12th ribbon graph expansion and I just classified it by topology, but this is a topological version of this theory if you want. But we want to do this where the infilling solutions are actually universes, JT universes. Okay? So we want to calculate, we want to have this structure, but we want to derive it starting with JT gravity. So the way that we do this is actually a trick that is, unfortunately for now, very specific to 2 dimensions. So 2D gravity, one example of 2D gravity is the Polyakov way of thinking about string perturbation theory. You couple 2-dimensional gravity to 2-dimensional matter, and you sum over the path integral, sums over the topologies. Now, you can actually do that to JT gravity. You can actually write JT gravity as the worldsheet theory of a string. And then the theory that describes the multi-string excitations, the multi-string scattering, which is precisely the thing that will tell you about such quantities, is its string field theory. Okay? So we don't do the first quantized string description that we usually do, let's say, in the textbooks. Instead, we go to, if you want, the more advanced textbooks, and we look at the second quantized version of this, which is the string field theory. So the string field theory of the worldsheet string, whose description is JT gravity, is precisely this universe field theory. And then what actually turns out to be very nice is that fixed energy boundary conditions are just the usual D-branes in string theory. So we have an interpretation of the multi-universe states as being the multi-string states, and we have an interpretation of the boundary conditions in terms of D-branes. And so now it's a matter of putting together these ingredients in order to establish this, generating functional. And then I want to show that it goes to the same symmetry breaking rigmarole as our effective field theory. Okay, so let me just do that. So the spectral determinants actually become insertions of these D-branes. I'm happy to tell you in private exactly how this works, but in view of time, let me just state it. So these determinant insertions, there are on the worldsheet just vertex operators of a particular twisted chiral boson phi. So when we want to have these determinant correlators in the string field theory, what we need to do is we need to calculate expectation values of these vertex operators. We can calculate them. But what we do is we don't actually explicitly calculate them. KS, by the way, stands for Kodaira-Spencer, which is another name for the string field theory that we've constructed here. So we just rewrite this explicitly, these correlation functions, as an integral over an n/n graded matrix. So there's some mathematical manipulation, which I believe is rather elegant, which explicitly rewrites this without any approximations as an integral over this flavor matrix. Now, previously I only showed you the 2/2. We can do it actually for n/n. And we can calculate this potential gamma of A. Then this here is this source term, x times A. So x are these insertions here. And you should think of these x's as roughly the energies, right? Okay, then what you do is you analyze the system and you show that it has precisely the same causal symmetry breaking scenario as the one that I showed you before. And it gives you the explanation of the ramp in the sense that you look at what actually does the 1/s² contribution mean on this side. Well, it's this two boundary wormhole that was expected. But interestingly, you can also do the second saddle point, and you can ask, what does that second saddle point mean? And it's essentially has to do with a different D-brane vacuum that this system is expanding around. So there is basically now an explicit gravity language to talk about precisely the causal symmetry breaking and its restoration, and therefore for each of the phases of this chaotic dynamics, I can tell you how do you understand this if you live on the JT worldsheet or in a JT universe. So this is, to me, is a gravity explanation of the ramp and a gravity explanation of the plateau, and maybe more abstractly, it's actually a way of generalizing this SSS duality between JT and the matrix model to the fully doubly non-perturbative level. And instead of connecting to the usual matrix model of SSS, we connect to this flavor matrix theory, and the flavor matrix theory is the right way to talk about these effects also from the point of view of quantum chaos. So we've been in quantum chaos always talking about this flavor matrix theory, and here we link it explicitly to a gravitational expression. So
here,
okay.
do you again take average over Hamiltonian?
Let's leave that for the questions, because I think this is a very, very important question. So what we do is actually very similar to what happened in the old topological string days with all these authors. So like Anagic, who I misspelled here, I'm sorry, Dijkgraaf, Klein, Marinho, and Baffa, and it's some sort of version of open-closed string duality, but our open string side, if you want, has to do with the chaos effective field theory, and the closed string side is this Kodaira-Spencer theory. And that's sort of interesting that we revived these old ideas, but by thinking about quantum chaos instead. And yeah, okay. I think, yeah, maybe as part of response to questions, for example, yours, I'll come back to these pictures. I don't want to explain them now. So let me just summarize. So this I already said at the halftime break, but I then said that there is a topological expansion of this chaos EFT, which maps to something like a wormhole calculus. And we can actually make it exactly the JT wormhole calculus by rewriting JT gravity in terms of this Caudaret-Spencer theory, which turns out to be a specific incarnation of this chaos effective field theory, which has more than just topological information. It also has information about the metric. Okay? And this is done by using this Caudaret-Spencer idea. It's an explicit realization of old ideas by Coleman, Giddings, Strominger, and more recently Marolf-Maxfield. I haven't talked about fluctuations, I haven't talked about higher dimensions, and I haven't talked about the causal symmetry break in higher dimensions. We can maybe talk about it as a discussion, but I think I'll leave it here. I'm already out of time. Thank you for your attention.
Are there any questions?
There was already one.
So do you want to answer that one?
Yeah, I do. It's actually, again,
Can you repeat it?
The question was, in this Caudaret-Spencer theory, if I may reformulate the question, am I averaging over the Hamiltonian or not? And the answer is, I wanted it to be no, but the answer is yes. And the reason is, if you want, one reason of seeing how this works is in these two pictures. So in this Caudaret-Spencer theory, there's actually two kinds of brains. There are compact brains and non-compact brains. The degrees of freedom on the non-compact brains are these A matrices, A, A, B. And in some sense, we can write down an effective theory of these A, A, B. This is sort of like, if you want, has a similar status as the DBI action for open string ending on non-compact B brains. But there is this other sector, which are the compact brains, which to some extent we have integrated out to get to this expression. But if I want to give them some meaning, those would be the Hamiltonian. So the strings that stretch from these brains that we integrated out to the same brains, which are not apparent in any of these, okay? Those would be, in my opinion, the Hamiltonian, and since we had to integrate them out to get to this effective theory, so what happens then is that these brains, they back react and they become geometry, and my JT strings basically float around in this geometry, but the geometry has been created by integrating out these H matrices. So in effect, we are averaging over the Hamiltonian, which is something I hope we would not find to be the case, but we have found to be the case.
So in the gravity discussion, there's been a lot of interest recently in how you go from a description that reproduces the smoothed ramp plateau curve to something that describes an individual theory.
Yeah.
So if I'm understanding correctly, the effective field theory here is producing something more like the smooth curve.
Yeah, that's another thing I didn't have the time to say very much. So that's also a different point of view, I think. But let me just say one more thing. So the game would be to try and freeze these degrees of freedom if we at all can. So to try and freeze the H degrees of freedom to one configuration and then see if we can still get some of this to work. But I don't know at this point how to do it. Now the fluctuations. So actually this effective field theory is a little bit more powerful than just saying it gives you the smooth function, because it actually allows you to calculate all the moments if you want. So what I calculated is I calculated the second moment of rho. But in fact, it tells you can also calculate the fourth moment, for example, and that would be the typical size of the fluctuation on top of this. And you can calculate the sixth moment and so on. Each of these map to a calculation in gravity in this way. So this is actually my comment here, which is that, is it really true? I would like to maybe propose that, at least in this formalism, the bulk gravity theory basically generates all the moments of the signal. So I'm not at this point anyway able to calculate the full signal, which would be something very erratic. But I am able to calculate the moments. And then the question is, if someone hands you all the moments, can you reconstruct from it the signal? Which I think is not always the case.
It's not clear to me it's the same thing, right? I mean, at the gravity level, what people are trying to do is to really produce some, like, you change the rules in the gravity theory to try to get something that reproduces a particular theory. And you calculate all the moments of the distribution, it still seems to me there's some choice involved in picking a particular representative distribution.
I'm not sure I understand your point completely, but that's not
Yeah, I think
that's not saying in a way that I think you're wrong. It's, honestly, I don't quite understand your point. But what I'm trying to say is that a possible scenario is that I can use this to calculate all the moments, and once I have all the moments, then I can still ask the question whether that satisfies me, whether in some sense all the moments is equivalent to having the full signal, meaning having the fluctuating curve, or it's not. And that's a question in statistics. So not every set of moments defines a probability density function that has those moments. So we could be in a situation where it doesn't.
Okay, maybe I can clarify my point. Suppose you know the probability density function exactly.
Yeah.
What I really want to know is the description of a particular draw from that distribution. Not the distribution, but
Yeah.
a Hamiltonian.
Yeah. So
seems like
my answer here, where I would have to freeze somehow the H matrix. I would have to freeze it to one configuration, and then I would have to try and go through this. I mean, naively speaking, in full honesty, it doesn't seem to be possible because you can't just freeze a D-brane.
Can I ask a follow-up on that? Oh, sorry.
Yeah.
In your EFT description, I think you said that if you integrate over the H's, then you get this nonlinear theory of the size, and that has a saddle point that breaks the symmetry and so on. And say you freeze the H, you can do that within your EFT problem.
Yeah.
Then do you still get the symmetry breaking phenomenology, or?
But only if I do something like a small average over energy windows or something. I do need to do.
You need to do something.
I do need to do some averaging.
Okay.
But that's the thing where, I mean, now I'm really speculating and I'm not necessarily completely consistent between every answer. So one thing, for example, is that you could also say that I don't actually know, I mean, there's no way that semi-classical gravity knows really about the microstates because they're totally out of reach of semi-classical gravity. So it's quite natural then that you don't know the exact spectrum. So this is where I talked about here the different reasons why you might want to do this averaging. Back too far. But for example, ignorance, right? So even if your theory is ignorant, now if someone hands you the n equals to 4 Hamiltonian, you need to make this theory somewhat ignorant. So for example, you could say, what happens if I go to the very high energy spectrum, like the microstates, record microstates, and I start averaging a little bit, because I couldn't possibly resolve that. That's already enough, even for an individual age. Okay? It wouldn't kill all the fluctuations, by the way, and there would be non-trivial higher moments. But it would be enough to give you the symmetry breaking pattern. In the symmetry breaking pattern, again, it doesn't say that you have smooth signals.
Right.
It's not saying that.
Is it a well-defined question to ask, given a particular H, is there a symmetry breaking phenomenology? Like, can I ask that question?
Yes, there is.
Okay.
But it is an extremely challenging question because, in fact, I've given talks before where I introduced it slightly differently. So it's an open conjecture in mathematical physics that every system that is classically chaotic, if you quantize it, has this Wigner description of energy eigenlevels. This is known as the BGS conjecture, Borrigas, Giannone, Schmidt. And in some sense, if you gave me a mathematically rigorous way of making precise what you asked, you would have proven that conjecture. Which would be great, of course.
So in quantum many-body context, this PKH is often discussed, but there is notion of locality, and if you look at local operators, so the full system, the universe is always in unitarily evolving, there is definite wave function, but locally the observables look like thermalized. So there is only one Hamiltonian, but it's the locality, the words that people use are that the rest of the system serves as a path.
Yeah.
But I don't know if there is any.
I think that picture is certainly it's certainly relevant, but whether so, I mean, I think that in ETH indeed people usually talk about locality, but you could also describe something where you just take subsets of degrees of freedom. They don't necessarily have to be related by locality. So, for example, when we talked about ETH in the SYK model, which actually I have here, we just took like let's say a pair of fermions.
Yeah, your different notion of.
But that's not local because the Hamiltonian is non-local. So I would say the more abstract notion that is relevant is that you take a subset, and the rest of the system, in some sense, acts as a bath for this subset effectively, up to small corrections that are suppressed by exponentials in the entropy. And that's certainly the relevant physical picture that's at work here. Yeah.
Yeah, so it's a different notion of locality. So SYK is all wall, but you just look at two local or four local where how many degrees of freedom are involved.
That's right.
And then you do not, but basically with averaging, it appears in a single Hamiltonian. You have intuition. It can appear in a single Hamiltonian. You do not need to average over Hamiltonian.
Correct, and that's also the scenario that you described.
Yeah. But somehow can in like your calculations some such notion of locality.
Well, it would be nice, but actually the calculations where we have most explicit results are unfortunately where, for example, in ETH we work quite a lot on SYK, so that doesn't address your question. And these random matrix things also not really systems where you have much locality. So I don't think I don't have any, let's say, way of proving ETH for some local quantum chaotic system. Yeah. Sure.
You mentioned that viscosity U22 divided by U1 and U1 has like 10 versions.
Yeah.
Now if you go to the n-mode computation, then you have a much more complicated process, like U and n divided by U1 to the power n.
But they're still symmetric, and they are still classified by those 10.
So it's known that there are only 10 versions of the more complicated process.
Yes, this is actually the Cartan classification. But where I think you fall out of it is when you have asymmetric ones, UN/M. But I don't yet know what role they play. So this is Cartan classified the 10 symmetric spaces, and actually the fermionic extension was then the cylinder, but it actually doesn't give you any units.
The other symmetric breaking patterns like UN broken to U2 times U1, that they don't matter. It always just breaks to U1 times U1 times U1.
Well, I don't want to make such general statements. I actually don't know really. I would think so, yeah. But we can look at the paper. There's actually a relevant paper for this.
Okay. It's great that there's questions, but I think we
Enough
should
is
get
enough.
to we should get to lunch because there is some more. Before first, let's thank Julian again. Also, apologies to our streamers. We get some technical issues, but we'll try to resolve them. As the saying goes, you can't make an omelet without cracking eggs. So please, if you're still watching, consider yourselves cracked eggs. And we're gonna have lunch, which is like 15 minutes away walk. So let's get to that.